Hello everyone, I am Poulumi Chakraborty, final year PhD student at Ohio State University. I'll be your session chair for this afternoon session. For the first talk, I am happy to welcome Professor Philipp Werner from University of Fribourg. He'll talk about non-equilibrium DMFT.
Okay, thanks very much. Thanks to the organizers for the chance to attend this nice spring school. I will discuss non-equilibrium dynamical mean field theory. That's a formalism which allows us to study the non-equilibrium properties of correlated lattice systems. And one of the reasons why we are interested in non-equilibrium dynamics is because experimental groups are exploring non-equilibrium properties of materials, typically using this type of pump probe setups where the material here is driven out of its equilibrium state by a strong laser pulse, the so-called pump pulse, and then the properties of the excited material are studied using weaker probe pulses which reach the sample with a well-controlled time delay. And nowadays the time resolution for these experiments is of the order of femtoseconds, which is the intrinsic time scale for electrons, for the hopping of electrons in solids. So one possibility is that by driving these materials into non-equilibrium states, one can disentangle competing or cooperative effects along the time axis if these competing effects have different intrinsic time scales. Even more intriguingly, there may be a possibility of tuning material properties by laser driving. A simple but important example is the insulator metal transition induced by photodoping. As you know, for example, from the phase diagram of cuprates, interesting quantum states can emerge if we dope charge carriers into a Mott insulator by chemical doping. So it's an interesting question, what kind of states can we realize if we produce charge carriers by exciting electrons across a Mott gap or charge transfer gap. And indeed, there are experiments which suggest that interesting phenomena can be found. A particularly ambitious goal is to create long-lived transient superconducting states. There is an example by the Cavalieri group, or several examples. The first one by Fausti was on a material where superconductivity is suppressed at a certain doping range by a competing stripe-ordered phase. And what they did is they excited the lattice degrees of freedom by a terahertz pump pulse, and then they showed that superconductivity emerges at temperatures where it is suppressed in equilibrium by this competing ordered phase. Also in fullerite compounds, there have been reports of light-induced superconductivity. So here I show you how the equilibrium conductivity changes if we go from above the equilibrium Tc to below the equilibrium Tc in case for AC60. So the equilibrium Tc is about 20 Kelvin. And you see that what happens is that in the real part of the conductivity, a gap opens up, and in the imaginary part, we see this 1 over omega divergence characteristic of superconducting states. And what was reported in these experiments is that similar changes can be transiently induced in the optical conductivity, even at temperatures far above the equilibrium Tc. There are also interesting experiments which have nothing to do with superconductivity. For example, the Mihailovic group in Ljubljana has shown that a polaronic Mott insulator, tantalum disulfide, can be switched into a metastable metallic state. And this metallic state is very long-lived. It can live for days if the material is cold enough. So here is a plot of the experimental resistance as a function of temperature. You see that below 180 Kelvin or so, we go into this polaronic Mott state where the resistance becomes very large. But then if one hits this material with a short laser pulse, one can switch it into this metastable metallic state, and then either by heating or applying further laser pulses, one can switch back into the equilibrium high temperature phase. And they have already developed a memory device based on this switching mechanism. And that's an interesting device in the sense that the switching speed is very fast. So this is a 30 femtosecond laser pulse. So the switching is orders of magnitude faster than in any semiconductor memory device. And also the energy consumption of this device is very low. So this example shows that by controlling the non-equilibrium properties of correlated materials, one may eventually find new important technological applications for these states. So that's motivation for us as theorists to look into these non-equilibrium properties of correlated materials. And so let me briefly summarize what are the challenges from the point of view of theory and numerics. So one obvious challenge is that we are dealing with strongly interacting many particle systems, which are already difficult to treat in equilibrium. The second challenge is that the laser pulses, which induce these interesting states, these are strong perturbations, so we have to treat these systems far beyond the linear response regime. And the least obvious, but nevertheless big challenge is that in the non-equilibrium dynamics, there are typically different relevant time scales which come into play. The excitation process typically happens on the time scale of femtoseconds. That's the hopping time scale of electrons in solids. Then if the laser pulse has many cycles, the material can transiently switch to so-called Floquet into a so-called Floquet state, where the behavior can be very different from that of the equilibrium system. Then after the end of the pulse, a relaxation process sets in, but this relaxation process typically proceeds in several stages. Often one finds initially a relaxation into a so-called pre-thermalized state, where, for example, the local observables look thermalized, while the non-local ones are still far from thermalized. If we have systems with long-range order, there can be slow dynamics associated with non-thermal critical points. And typically the full thermalization happens on timescales which are orders of magnitude longer than the timescales needed to describe the initial excitation process. And so bridging all these timescales in a single simulation is very challenging. And what I'm going to describe today is the non-equilibrium dynamical mean field formalism, which is one of the powerful formalisms that allows us to get relatively far along this time axis and to describe many of these interesting phenomena. So here's a kind of overview of the talk. I will start with a basic introduction into the dynamical mean field formalism and its cluster extensions, and then I describe the non-equilibrium extension of this formalism, and also say a few words about how we solve in practice the non-equilibrium DMFT equations. And then I will illustrate this formalism with two small examples. One is a AC field quench example, which demonstrates that we can tune the interaction in a correlated electron system by laser pulses. And I will then also discuss eta pairing in photodoped matte insulators. That's an example of a non-thermal superconducting state which exists at very high energy. So let us start with something that everybody knows. That's the static mean field theory for the Ising model. So we have a lattice of interacting Ising spins, and in mean field theory we map it to a single site effective model, which describes a single spin in an external magnetic field. So we can focus on one of the sites that becomes our spin, and then the rest of the lattice is replaced by this effective magnetic field. And we solve this problem in a self-consistent manner by imposing that the lattice magnetization is the same as the magnetization obtained from this single-site effective model. Dynamical mean field theory is an attempt to devise a similar type of mean field description for a correlated fermionic lattice model like the Hubbard model. Again, we map the lattice problem to a single-site effective model, but this model is more complicated. It is a so-called quantum impurity model where we have one correlated site embedded in an uncorrelated path of electrons. So we focus on one of the sites of our lattice that becomes our impurity site, and the rest of the lattice is replaced by a bath of non-interacting electrons, and then we optimize the parameters of the bath in such a way that local observables between the lattice and single-site description match, or more specifically in such a way that the local lattice Green's function is given by the impurity Green's function. And in order to be able to close this self-consistency loop, we have to make an essential approximation, and that is that we neglect the momentum dependence of the self-energy of our lattice model and assume that this self-energy is given by the impurity model self-energy. Now, in many practical calculations, we integrate out the bath and replace it by a hybridization function in action formalism, and this hybridization function describes how the electrons hop in and out of this impurity site as a function of time. And this hybridization function is the function which is optimized in the self-consistency loop and which plays the role of the mean field in this theory. And because it's a time-dependent function, we call this mean field theory a dynamical mean field theory. Now, here are the steps in a dynamical mean field theory calculation. We start from an initial guess for the hybridization function. Then by some numerical impurity solver, we calculate the Green's function and the self-energy for our impurity model. Then we make this essential approximation that the self-energy is local and given by the impurity self-energy. And with this, we can then calculate the lattice Green's function and also the local lattice Green's function. And finally, we impose the self-consistency condition that the local lattice Green's function is the same as the impurity Green's function. And with this, we can extract a new hybridization function. And then we iterate this loop until convergence is reached. Let me also briefly say that within dynamical mean field theory, we can easily treat systems with two sublattice type order, such as antiferromagnetic states, for example. In this case, the bath for sublattice B is given by the local Green's function for sublattice A and vice versa. And then if there is a pure Néel type order, for example, then we know that the bath for sublattice B and spin up is the same as the bath for sublattice A and spin down. And this allows us to collapse the two coupled self-consistency loops into a single self-consistency loop where at some point we swap the spin in the self-consistency loop. Yeah. Here is a sketch of the generic phase diagram that we get for the Hubbard model in dynamical mean field theory. You see that at low temperature, there's a first order phase transition from a metallic state to a Mott insulating state. Whereas at high temperature, there's a smooth crossover between these two phases. This is for the paramagnetic calculation. If we suppress antiferromagnetic order, if we allow for antiferromagnetic order, then the first order transition disappears inside antiferromagnetic insulating dome, and we only see a crossover from a weak coupling Slater type antiferromagnet to a strong coupling Heisenberg type antiferromagnet. Also, at half filling, there is a transformation which allows us to map the repulsive Hubbard model onto the attractive Hubbard model. And so the phase diagram on the attractive Hubbard model side looks exactly the same, but in this case, antiferromagnetism is replaced by S-wave superconductivity, and this later to MOT crossover is replaced by the BCS to BEC type crossover in the superconducting phase. Now, dynamical mean field theory can be shown to be an exact description in infinite dimensions. In this limit, this assumption of a local self-energy becomes exact. However, the theory is only approximately correct in lower dimensions, and in particular, the neglect of spatial fluctuations becomes problematic in dimensions smaller than 3. However, the 2D Hubbard model has been studied a lot in connection with cuprates, because this model more or less describes the physics of the copper-oxygen planes in cuprates. So early on, the dynamical mean field theory formalism has been extended to a cluster dynamical mean field theory. For example, if we want to study phenomena such as the pseudo gap, which has to do with antiferromagnetic short-range correlations, or also if we want to describe a D-wave order parameter, we need at least 4 sites, and so we can extend then the impurity model into a cluster impurity model in order to capture this kind of physics. And there are different flavors of cluster extensions. One is the so-called dynamical cluster approximation, where we periodize the cluster impurity problem, and this corresponds to a coarse graining in momentum space. So the self-energy becomes a piecewise constant in momentum space. In the single-site DMFT calculation, we have no momentum resolution, so the self-energy is completely flat in the Brillouin zone. In a 4-site dynamical cluster approximation calculation, we would decompose our Brillouin zone into 4 patches, and then the self-energy can take 4 different values in principle on these 4 patches, and in an 8-site cluster calculation, we would decompose it like this. And by going to larger and larger clusters, we can capture more and more longer-ranged spatial correlations. The self-consistency loop in this dynamical cluster approximation looks very much the same as in single-site dynamical mean field theory, except that we go through this loop one momentum patch at a time. So we also average over only a single momentum patch, and we impose the self-consistency condition for each patch separately. And the only place where the different momentum patches are coupled is in the solution of the cluster impurity problem, because we have a local Hubbard interaction which couples different momentum sectors. But apart from this, the self-consistency loop looks exactly the same. So it's conceptually easy to extend to these cluster problems, but of course numerically the calculation becomes quickly very heavy. Okay, now let us discuss how to extend this formalism to non-equilibrium problems. And for this, I need to introduce the concept of a Kadanoff-Beim contour. So let's assume that the initial state of our system is described by a density matrix rho 0, where 0 here means time 0. Then our state at some other time t is obtained from this rho of 0 by multiplying with time evolution operators on the left and the right, where the time evolution operators are these time-ordered and anti-time ordered exponentials. And with this time-evolved density matrix, we can then calculate observables at some time t as the trace of rho of t times this observable. Now let's insert the expression for the density matrix into this trace here and use the cyclic property of the trace to move this red time evolution operator to the right-hand side. And then we obtain this expression here. And now we replace the time evolution operators by these time-ordered and anti-time ordered exponentials. And we can also write the initial density matrix as an imaginary time-ordered exponential. And now you see that the calculation of the expectation value at time t involves the propagation along such a three-legged contour in the complex time plane. Namely, we start at time 0, we propagate forward in time along the real-time axis up to time t. Then we measure the observable. Then we propagate back along the real-time axis with this blue time evolution operator. And finally, we propagate along the imaginary time axis to minus I beta, where beta is the inverse temperature of the system. And this imaginary time branch here represents the initial equilibrium state of our system. To simplify the formalism, one can introduce the so-called contour ordering operator, which orders creation and annihilation operators along this three-legged contour as indicated by these arrows. And with the help of this operator, we can then simply write the time-dependent expectation value as such a contour-ordered expectation value of our observable. And this formalism can then be generalized to two-point correlation functions A of t, B of t prime. That's also a contour-ordered two-point correlation function. And the two-point function which is particularly relevant for us is the Green's function, which is now the contour-ordered expectation value of d dagger and d, where d is the impurity model annihilation operator. Now, because the creation and annihilation operators can be on three branches, we have in principle 9 components in our Green's function, and they indeed can be different. For example, the component G12, where the annihilation operator is on branch 1 and the creation operator is on branch 2. This is different from the component G21, where the annihilation operator is on branch 2 and the creation operator is on branch 1. Because if we think in terms of the contour ordering, you can see that in this case, the black dot comes before the white dot, and in the other case, the black dot comes after the white dot. So these are two different Green's function. However, not all of them are different. For example, the last operator on our contour, we can always shift between the upper and lower branches, because the forward propagation from here and the backward propagation will cancel. So for this reason, we have that G21 is equal to G22, and there are similar other redundancies which allow us to eliminate 3 out of these 9 components, and then we end up with 6 physical components which have names like retarded, advanced, Keldysh, and so forth. And they are then related to the spectral function or the occupation of our system. Okay, now what is non-equilibrium dynamical mean field theory? Non-equilibrium dynamical mean field theory is nothing else than dynamical mean field theory implemented on this Kadanoff time contour using these non-equilibrium Green's functions. So in particular, the mapping from the lattice model to the impurity model is the same as in equilibrium, and also all the steps in the self-consistency loop are the same as in equilibrium. Nevertheless, this type of calculation is much more challenging than an equilibrium DMFT calculation. So why is this the case? One reason is that you see that these functions, the hybridization function, Green's function, self-energies, these are now functions of 2 separate time arguments, t and t prime, and not functions of time differences as in equilibrium. And that is because we lose time translation invariance in a general non-equilibrium state. So we have to deal with basically matrix objects rather than vectors, and that is, for example, much more difficult to store. Also, the solution of a Dyson equation, which is very easy in equilibrium by going to Fourier space, becomes more complicated. Out of equilibrium, we cannot explicitly calculate this inversion, but we have to rewrite this Dyson equation as an integral differential equation on this Kadanoff-Beim contour, three-legged contour, and then solve this with appropriate numerical techniques. But in principle, at least conceptually, everything extends very straightforwardly to the non-equilibrium domain. Also, the cluster extension can be formulated in principle directly for non-equilibrium problems by using these non-equilibrium Green's functions. But of course, the calculation also then becomes very heavy if we have to deal with cluster impurity problems. As always in the dynamical mean field calculations, the main challenge is the solution of the impurity model. So this is a general now non-equilibrium impurity model where we have some local part describing interaction and chemical potential terms and the hybridization part. And the hybridization part, depending on the formulation, can be rewritten also in terms of a non-interacting impurity Green's function or Weiss Green's function, which is equivalent in terms of information to the hybridization function. And then given such a impurity action, we have to calculate the impurity Green's function by calculating these types of expectation values. Now, let me just very briefly sketch three different techniques which have been used as impurity solvers in such non-equilibrium calculations. And as the first example, I showed the adaptation of the weak coupling continuous time method to non-equilibrium problems. So let's go back to our expression for the time-dependent expectation value of observables. And now in this method, I will switch to an interaction representation where the time evolution between operators is given by the quadratic part of the Hamiltonian. The part h0 gives the time propagation between operators. And in this interaction representation, what remains in the exponent of the time evolution operators is the interaction part of our Hamiltonian. And what we can then do is we can expand these time-ordered exponentials in powers of the interaction term, and then at a given order in the expansion, we get some kind of random collection of interaction Hamiltonians on our three-legged contour. And because the time propagation from one of these operators to the next is given by the quadratic part h0, we have a Wick theorem, and we can integrate out the Bath degrees of freedom, and then we end up with these kind of weak coupling diagrams where we have interaction vertices connected by these non-interacting Green's function lines. And then we can add up families of such diagrams into determinants and then sample these determinants as we do in equilibrium continuous time Monte Carlo. However, some of you may notice that there's a potential problem with this. You can see that the operators on the real-time branches, they come with factors minus I, and also these Green's functions are complex functions. So the weights are complex, and so we have to do Monte Carlo sampling with complex weights. That gives us a sign problem, and this sign problem becomes more and more severe the longer this contour becomes, and the higher the perturbation order will be on the real-time branches of the contour. And in practice, this means that we are limited to relatively short times so that the perturbation order on the real-time branches is not too high. But okay, it works, and at least for short contours and not too strong interaction, we can obtain numerically exact DMFT results. So here are results for the double occupation after an interaction quench from the non-interacting Hubbard model to some kind of weak to intermediate coupling regime. And on the right-hand side, we see the result for quenches to the strong coupling regime. And here you can clearly see that, okay, we cannot really see the full thermalization of the problem because we have to stop at some point because the sign problem becomes too severe. But yeah, at least for short times, this is a method that gives us the exact non-equilibrium DMFT solution. Often it is desirable to go to longer times at not so heavy computational cost. So what one can do is, for example, weak coupling perturbation theory, where we approximate the impurity self-energy, for example, by a second-order diagram, as shown in this figure on the top. And then we plug this self-energy into an impurity model Dyson equation to generate then a subset of weak coupling diagrams for the impurity Green's function. And this set of diagrams just contains all of these second-order self-energy insertions. So that's the bare second-order perturbation theory. We can also boldify these diagrams by replacing the Green's functions in these diagrams by the interacting Green's functions that corresponds to summing up a larger class of diagrams, but more diagrams does not necessarily mean a better approximation. Here we compare this bare and bold IPT, iterated perturbation theory approximation to the numerically exact Monte Carlo results. So the colored dots are the Monte Carlo data. The full lines are the boldified second-order perturbation theory data, and the dotted lines are the bare second-order perturbation theory data. What we can see from this are two things. So a nice aspect of the boldified theory is that it is a conserving approximation. So it, by construction, conserves the total energy after an interaction quench, which is a nice property that is not shared by the bare perturbation theory, which is not conserving. So this one breaks down eventually, energy conservation breaks down at strong interactions. On the other hand, if we look at the short time dynamics, even in the strong coupling regime, we see that the bare perturbation theory is actually more accurate than the boldified theory, which strongly overestimates damping effects. So yeah, if we restrict ourselves to short times or weak interactions, then the bare perturbation theory is preferred. But yeah, this shows that all these approximate methods have basically some weakness. For the study of strongly correlated systems, in particular Mott systems, a different type of perturbation theory turns out to be very useful, strong coupling perturbation theory. In this theory, we introduce so-called pseudoparticle Green's functions for each atomic state. So basically for the single orbital Hubbard model, we have the four states on the top there, the empty, the upspin, the downspin, and the doubly occupied state. And then for each of these states, we define a so-called pseudoparticle Green's function, and the self-energy then for these pseudoparticle Green's functions, which at the lowest order looks like this, a product of a a hybridization function and the pseudoparticle Green's function. So that's the lowest order. And with this, if we plug this into the pseudoparticle Dyson equation, we can generate basically the subset of hybridization expansion diagrams which do not involve any crossing hybridization lines. And that's why this approximation is called the non-crossing approximation. And then at the next order, we can add the diagram which has one crossing in the hybridization lines. And then with this, we generate the whole subset of hybridization expansion diagrams, which contains at most one crossing in the hybridization lines. And that's why this is called the one crossing approximation, and then we can push this to third order and fourth order. And that's a nice method in the sense that in the strong coupling regime, it systematically and quickly converges to the exact result. So here's again a test against the Monte Carlo data. The dots, the blue dots are the Monte Carlo data for interaction quenches, and I show again the double occupation. And you see this is the non-crossing approximation. The green one is the one crossing approximation. The red one is the third order approximation, and this converges very fast to the correct result in the strong coupling regime. So let me just say a few words about recent developments in the impurity solver field. So one challenge in these diagrammatic approaches is that as we go to higher and higher orders, the cost escalates because, first of all, the diagram topology, the number of diagrams increases very fast. And also for each of these internal vertices in the diagrams, we have to integrate over the three-legged contour, and that's computationally heavy to perform high-dimensional integrals. But there are new ideas how to do this efficiently by combining so-called quantix representation with tensor cross interpolation. So let me briefly say what this is. So in the first step, we can basically, if f is the integrand over which we have to integrate to get our self-energy, then we can replace the arguments of this integrand by a binary representation, which introduces the binary bits of these variables as arguments. And our function then becomes a high-dimensional tensor whose legs are the bits of this binary representation. And this is equivalent to a wave function of a spin 1/2 chain. And people working with quantum spin systems, they have known for a long time that an efficient representation of such a wave function is a matrix product state. So we do now the same thing. We express our function in this binary form by a matrix product state. And this allows to highly compress the function and to reduce the memory demand for these functions very much. And the second advantage is that now we have an approximately factorized form of our function, and so we can express our multidimensional integral in this factorized form as a product of one-dimensional integrals. And that is much more easy to evaluate, and so that is what gives us a significant speed up in these calculations. And so using these techniques, we will be able to go to higher order diagrammatic calculations and basically approach numerically exact solutions in many interesting parameter regimes. So let's now test the dynamical mean field formalism itself. So DMFT in low-dimensional systems is by itself an approximation. So let's see how severe is this approximation. And to test this, we have studied, first of all, a one-dimensional Hubbard model, an interaction quench in a one-dimensional Hubbard model. And here we have a good method, the density matrix renormalization group method, which can give us exact reference data, at least for short time dynamics. And so this is a comparison for a quench from U0 to a small interaction. That's again the double occupation. And we compare the evolution in DMFT, that's the red line, to the exact reference from the DMRG calculation. And you see it looks okay, but not very good. And that's to be expected because the one-dimensional case is the most challenging case for DMFT, because we know that spatial correlations are very important in one dimension. But as I explained at the beginning, we can extend systematically our DMFT approach to cluster DMFT. And here you see the results for 4-site, 8-site, 16-site cluster calculations, and you can see that we can now systematically kind of approach the exact reference data. So by going to these clusters, we can capture more and more of the non-local correlations and then get the more accurate time evolution, at least up to a certain time. So that in principle provides a way to approach the exact solution, although in practice it's of course numerically heavy to do these cluster simulations. Now in higher dimensional systems, it's very difficult to find any benchmarks. There are basically no other methods which can provide us with benchmark data. So what we did here is we benchmarked against the cold atom simulator. So cold atom people can implement a Hubbard model in their lab, and some groups like Esslinger group at ETH, they can also mimic electric fields by shaking their lattice. And so what we did here is we checked, or we compared DMFT for the resonantly driven Mott insulating Hubbard model against such a cold atom simulator. And what is done in this calculation is that the driving field is ramped up linearly in the amplitude of the field, and we measure the double occupation after the end of the ramp for different amplitudes of the driving field. So the different colors are the different amplitudes of the field, and this is the ramp time. And basically for short times, we should be able to directly compare the experiment to the DMFT calculation because there are no free parameters. So we implement in the DMFT the same lattice, the same density, the same ramp protocol. And you see for short times, it works well. For longer times, there are discrepancies because there's a trapping potential in the cold atom system, and there's at long times then redistribution of atoms in the trap and also atom losses. This is not captured in the calculations. But within these error bars, you see there's almost perfect agreement between experiment and theory. And I should say these error bars are not error bars of the DMFT calculations, but these are error bars of the experiment. So in the experiment, they have to estimate somehow the initial entropy of their system, and that involves a certain amount of modeling and assumptions. And these error bars represent the uncertainty that comes into this through this estimate of the initial entropy in the experimental system. But apart from this uncertainty, you see there's perfect agreement between these two examples, which gives us some confidence that non-equilibrium DMFT is a powerful tool which can give us quantitative results for highly non-equilibrium states in strongly correlated systems. And so with this, I now switch to the two small examples that I want to discuss. The first one is a simple but nice example, namely an AC field quench in a weakly correlated metallic Hubbard model. So we have a Hubbard model with small interaction U, and then we suddenly switch on an electric field with amplitude E and frequency omega. And then we measure the double occupation as a function of time. And I should say that this is a calculation based on a Monte Carlo impurity solver, so these are exact DMFT results. And what we see here is that for small values of the field, the double occupation goes down, which indicates that the interaction effect increases through the action of the field. On the other hand, for stronger amplitudes, you see that the double occupation goes up, and eventually it crosses this threshold of 1/4, which in equilibrium is the highest double occupation that we can get for positive temperatures in a repulsive system. So if we cross this threshold, it indicates that somehow the interaction has been switched from repulsive to attractive. And that's an interesting prospect, because we know that the TC in the attractive Hubbard model is far higher than the TC in the repulsive Hubbard model. And at least one order of magnitude higher. So if we could switch the interaction in a correlated electron system to attractive, we would expect a potentially very high temperature superconducting state. Now, how does this come about? This we can explain by looking at the one-dimensional system with a field pointing along this chain. So let's assume the field has this cosine form with amplitude E and frequency omega, then the vector potential from which this field is derived has a sine form with this prefactor E over omega, and that's why this ratio of E over omega plays an important role in this analysis. Now the field enters the calculation through the so-called Peierls substitution. That is, we shift the momentum of our dispersion by the time-dependent vector potential. And now a good idea for what is going on can be gained by averaging this time-dependent dispersion over one period of the driving field. That's this average dispersion. And what we find for this is that it is the same as the original dispersion, but it is renormalized by a Bessel factor of field over omega. And the Bessel function is sketched here. It has sign changes, and these sign changes lead to the inversion of the interaction. So let's illustrate this with a very kind of simple sketch. So this is our half-field cosine band of the initial equilibrium state. Now, if we come in with the AC field, we start to wiggle electrons back and forth within this band. And by time averaging, we see that the band will be renormalized a little bit. And that's the renormalization factor by this Bessel function here. And then if we wiggle more, if we have a stronger electric field, the band will be more strongly renormalized. And eventually, if the field amplitude is strong enough, we will invert the band with the population still stuck in the same place. And such a state where we have the high energy states occupied and the low energy states unoccupied corresponds to a negative temperature state. So population inversion corresponds to a negative temperature state. Now what we have to understand is that a system with a repulsive interaction and a negative temperature is equivalent to a system with an attractive interaction and a positive temperature. And to see this, let's take the system with the inverted band and the negative Bessel factor and this inverted population, so the negative temperature. And then let's look at the density matrix for this problem. And what we can do is we can pull out this negative Bessel factor to get the positive effective temperature, but then we have to divide the interaction by this negative Bessel factor, and that gives us this effective negative interaction, which leads to the enhancement of the double occupation and potentially to the emergence of a superconducting state. So that's one small but interesting example which shows how non-equilibrium driving can potentially induce interesting phases. Now, as a second and last example, I want to discuss the so-called eta pairing state in strongly repulsively interacting systems. And here I show a result from the work by Achim Rosch and co-workers who, in the context of cold atom calculations or studies, considered the Hubbard model with basically infinite interaction and with full photodoping, in the sense that every side of this Hubbard model is either doubly occupied or empty. And he showed that this state can be superconducting with a staggered order parameter. And just to clarify what is the difference to the equilibrium superconducting state, the equilibrium superconducting state, for example, in an attractive Hubbard model, has a uniform order parameter, same value on each lattice side, whereas this superconductor, which is realized in this strongly repulsive photodoped MOT system has a staggered order parameter which changes sign between the two sublattices. And we call this kind of superconducting state eta pairing state. Yeah, we can, maybe I'll skip this. We can basically integrate out in the Hubbard model all the terms which change the number of doublons and holons in the system, and then map this infinitely repulsive model to a spin system with so-called eta spins, where eta spin up means there's a doublon on the site, and eta spin down means there's a holon on the site, and the superconducting state with staggered order in this language corresponds to a ferromagnetic order in the XY plane. But yes, let's maybe discuss this afterwards if you are interested in the details. Now, a few years ago, more in the condensed matter context, Kaneko and co-workers studied a one-dimensional Hubbard model, and they showed that by applying suitable laser pulses to this one-dimensional Hubbard model, they can induce such a eta pairing state. And here is the evidence. The blue curve here shows the pair-pair correlation function in the equilibrium system. So it decays as a function of distance, whereas after the laser pulse, you have these kind of staggered, non-decaying pair-pair correlations, which is suggestive of the realization of such a eta pairing state. And using dynamical mean field theory, we have also studied this eta pairing phase. Here's a very recent result where we kind of mapped out the temperature doping phase diagram of the photodoped Hubbard model and compare it to the equilibrium chemically doped Hubbard model. So this dome here is the TC of the D wave solution for the repulsive Hubbard model. It has a TC of about 100 Kelvin. The red line is the TC of the attractive Hubbard model, which is far higher, as we said before, but attractive Hubbard model is hard to realize in a condensed matter system. And this blue one is the TC of this eta pairing phase in a photodoped MOT insulating Hubbard model. So you can see it can reach very high temperatures, even for moderate photodoping. So maybe in reality, we can reach something like 10–15% photodoping, but we can still be far above room temperature for the effective temperature of the doublons and holons and have this superconducting state. So if we assume, for example, that there's energy dissipation to a cold lattice, we may easily reach this type of electronic temperature. So what is the effective temperature of a photodoped MOT state? Basically, for the doublons, these are the doubly occupied sites which occupy the upper Hubbard band. There is some energy distribution which we can fit to a Fermi distribution to define the doublon temperature. And similarly for the holes, we can fit the distribution to a Fermi function and define the temperature of the holes. And that's the effective temperature, which can reach these very, very high values of more than 1000 Kelvin. What are the spectroscopic signatures of such an eta pairing state? So here are the spectral function of this system in the eta pairing phase and in the normal phase. So in the eta pairing phase, there is a gap opening at these effective Fermi levels for the doublons and the holons. And the other thing that is noteworthy is that you see that the bands themselves are much sharper in the eta pairing state than in the non-superconducting state. So as we go into this eta pairing state, the electrons become much more coherent and we get a sharpening of the bands, which would be visible, for example, in photoemission spectroscopy. Then in optics, we can measure the optical conductivity. And here you see then also characteristic changes between the normal state, which has a Drude-like feature in the real part, to the eta pairing state, which has kind of a gap in the real part and the 1/omega divergence in the imaginary part. You can see that since these are non-equilibrium states, we have also negative real part of the negative conductivity at high energy. So these are the energies corresponding to the MOT gap So at these energies, we can trigger double and Holland recombinations, which correspond to energy gain. And that's why we have a negative conductivity. But that's the case both in the normal state and in the eta pairing state. But what is characteristic for the eta pairing state is the opening of the gap. And this 1 over omega divergence. And so let's compare this to the experiments. For example, on K3C60, you can see that it looks very similar. They also report actually negative conductivities in some of their experiments. And of course, this 1 over omega-like divergence. So this begs the question, can eta pairing play a role in these experiments? I think it's an open question. So one obvious difference is that these experiments are on metallic states or metallic systems. K3C60 is a metallic system. Also, the doped cuprates, which we are used for such experiments, are metallic systems. And in such systems, we don't have long-lived doublons and holons, which we need conventionally to realize an eta pairing state. But it's possible that at least transiently, we can realize an eta pairing state for a very short amount of time, even in a metallic system, if we can somehow create sufficiently cold doublons and holons. And that's something that we are currently studying in my group. And yeah, hopefully we have some data about this in the near future. And with this, I'm done. I just list here 3 review articles, which are useful if you want to read up on this topic. So that's the old review by George and co-workers on DMFT, which is still a very good reference. More than 10 years ago, we wrote this review on non-equilibrium DMFT, which I think describes the whole formalism and non-equilibrium Green's function formalism very nicely. And very recently, we wrote a review article more specifically about photo-induced non-equilibrium states in MOT insulators. There are many interesting phenomena which can be realized in photodoped MOT systems. And if you are interested in that, please have a look at this recent article. And here I acknowledge all the many former postdocs who have contributed to this work. And I thank you for your attention.
Questions?
Thank you for the very nice talk. I just wonder, you show some signatures in optical conductivity and also the spectral function. Is there any fingerprints in higher harmonic spectra?
Well, yeah, I mean, we haven't looked specifically at the fingerprints of the eta pairing state, but of course, if you have gap opening or changes in the gap size, that will be reflected in high harmonic spectra. I mean, we have studied a lot the high harmonic spectrum of MOT insulators. And basically, yeah, the cutoff energies in the high harmonic spectra are given by the gap size. So if you have the opening of a gap, as I showed for this eta pairing state, it would be reflected, of course, in the high harmonic spectrum.
Thank you for the talk. I'm quite interested in this eta pairing stuff. And I'm wondering, what is the definition of the spectral function you showed here? Because like I don't really know what is the meaning of the spectral function in the non-equilibrium sense.
Well, I mean, it's the same as in equilibrium. It's the amplitude for removing or adding electrons. Yeah, for the occupied states, it's the electron removal probability. And
so are these poles or the sharp peaks still representing some excitation or?
Yes. I mean, basically, I mean, the upper Hubbard band basically represents doublons, doubly occupied sites, which can propagate through the system. And what is different now in this non-equilibrium photodoped state is that we really have a large population of these doubly occupied sites. And similarly, I mean, the the lower Hubbard band represents the singly occupied states, and if we dope holes into the lower Hubbard band, these are the charge carriers which can move around, the hole-like charge carriers which move around in the background of the half-filled Mott insulator. And that's the same thing now for the photodoped state, except that we have a lot of these holes, much more than we would have by quantum fluctuations in the equilibrium state. But yeah, I mean, the only difference to the equilibrium system is that we have now two Fermi levels. We have a Fermi level for holes, and we have a Fermi level for doublons. And they, in principle, also can have separate temperatures. And actually, one thing maybe I should mention about this is that so this is now calculated with one of these high-order real-time non-equilibrium solvers for a steady-state situation. And of course, we can use the same solvers for equilibrium problems. So I think in the future, at some point, we will not need any analytical continuation or anything anymore, but we can just solve the spectral function on the real axis and obtain nice results like this.
Question? Yeah.
Hi, thanks for the great presentation. I have a bit of a more general question about the self-consistency condition, and if the question of uniqueness, having a unique solution for the self-consistency condition matters, and are there regimes where you see a non-uniqueness in real time?
Yeah.
And is that a physical thing or a technical artifact if it's not unique?
I mean, yes, that's a good question. In equilibrium, this has been studied a lot. And for example, in DMFT, in DMFT for the single band Mott insulator, there is indeed a coexistence of two solutions. So there's around this line, there is basically a coexistence of a metallic and a Mott insulating solution. And this line is basically where the free energies of these two solutions cross. And now it's a very good question if there's some kind of non-equilibrium protocol where we could, for example, switch into the metastable coexisting solution. And we have tried this. We have been looking for this. We haven't found it, but I think it has to do with these approximate impurity solvers. So if we use, for example, non-crossing approximation for impurity solver that is heavily biased towards the insulating solution, and then it's not easy to switch to the competing metallic solution. So, but I think with now more accurate higher order solvers, one should revisit this. I'm sure there is a possibility with exact solvers to switch to metastable coexisting states.
Thank you. Great answer. Thanks.
Okay, let's thank the speaker. Yeah.